It's everywhere, but we often take it for granted. It's a silent messenger that races across space, telling us stories about the universe. Every sunset, every rainbow, every star in the night sky. They're all whispers of light, revealing secrets, if we know how to listen. Take a moment to imagine this. A distant world, thousands of light years away. It's locked in perpetual twilight, its surface lashed by storms of metallic rain. We know of this alien world, not because we've seen it directly, but because of the light that escapes its atmosphere and travels to us. By analyzing that light, scientists can decode the chemicals swirling in its clouds, the composition of its atmosphere, even the potential for life hidden beneath its raging skies. This ability to interpret light's language didn't spring from some high-tech lab or futuristic telescope. It began in the most humble of settings, a small dark room where a man named Alhazen pierced the wall to let in a single ray of sunlight. Imagine standing in a room in 11th century Basra, Iraq. The desert sunlight streams through a tiny hole in the wall, casting an inverted image of the world outside onto an opposite surface. To most, this might seem like a curious trick of nature. To Alhazen, known in his time as Alhazen, it was the key to understanding how we see. Born in 965 CE, during the Islamic Golden Age, Alhazen grew up in a world where scholarship flourished. Ancient Greek texts were being translated into Arabic, sparking advances in science, philosophy, and mathematics. Alhazen's curiosity led him to question the works of revered thinkers like Ptolemy, who claimed that vision occurred because the eyes emitted rays of light. To Alhazen, this explanation didn't align with what he observed in nature. Instead of relying solely on theory, Alhazen turned to experimentation. He conducted groundbreaking studies of light and shadows, using tools like mirrors, polished surfaces, and water-filled vessels to investigate how light moves and bends. His experiments culminated in his masterpiece, the Book of Optics, a 7-volume treatise that defined how humanity understood vision. Alhazen showed that light travels in straight lines and enters the eye where it forms an image, much like the camera obscura he used in his studies. His meticulous observations also explained reflection and refraction, laying the groundwork for modern optics and even the scientific method itself. What's remarkable about Alhazen isn't just his discoveries, it's his approach. He believed that science should be based on observation and proof, not speculation. Centuries before the Renaissance, he was already practicing the principles of experimentation that would guide figures like Galileo and Newton. Alhazen's insights opened the door to seeing the world differently, literally. But before humanity could gaze into the cosmos through a telescope, it had to master what went inside it. The humble lens, a curved piece of glass, would become the next step in the journey to understanding light. Before humanity could gaze into the heavens, we needed a tool that could bend light just right. That tool was the lens, a seemingly simple piece of curved glass. But crafting lenses clear enough to reveal the invisible took centuries of experimentation, skill, and ingenuity. In the 13th century, Italian artisans began grinding glass to make spectacles, a simple invention that changed how people saw the world, literally. By the late 16th century, Dutch craftsmen like Hans Lippershey and the Janssen brothers refined the art of lens making. Their grinding and polishing techniques created lenses that magnified the unseen, paving the way for 2 groundbreaking instruments, the telescope and the microscope. Galileo Galilei is famous for pointing an early telescope skyward in 1609, using lenses to shatter old beliefs about the universe. He discovered mountains on the moon, Jupiter's moons, and the phases of Venus, all evidence that the Earth wasn't the center of the cosmos. But lenses weren't just for the stars. Around the same time, scientists were turning them inward to explore the tiniest details of life. One of these pioneers was Marcello Mapici. Using an early microscope, He revealed structures no human had ever seen: capillaries, the tiny blood vessels that linked arteries and veins. In 1661, Malpighi's discovery proved William Harvey's theory of blood circulation and laid the foundation for modern biology. The same lenses that brought distant worlds into focus also unveil the intricacies of our own. Whether it was Galileo observing the heavens or Malpighi studying tissues, these simple pieces of glass transformed how we understand both the universe and ourselves. And as the art of lens making advanced, so did humanity's ambition to look further and deeper. This pursuit of precision would soon lead to an even greater discovery, as light became the ultimate tool for exploration. By the mid-17th century, humanity had mastered the art of bending light through lenses to explore the vastness of space and the microscopic intricacies of life. But Isaac Newton took a bold step further. He wanted to unravel the nature of light itself. So in 1666, Newton carried out a deceptively simple experiment in a darkened room. Using a glass prism, he split a beam of sunlight into its vivid spectrum of colors: red, orange, yellow, green, blue, indigo, and violet. It was a breathtaking display, but Newton wasn't satisfied with the spectacle. He wanted to know, was this rainbow created by the prism itself, or was it hidden in the sunlight all along? To test his theory, Newton placed a second prism in the path of the spectrum. Instead of scattering the colors further, this second prism recombined them into pure white light. The conclusion was revolutionary. White light wasn't a single entity, it was a blend of all colors, and the prism merely revealed what was already there. Newton's prism experiments laid the foundation for spectroscopy, the study of light's interaction with matter. He showed that light could be split, analyzed, and understood in new ways, proving it was far more complex than anyone had imagined. But Newton's work wasn't just about rainbows. It was about revealing the hidden. Just as Galileo's telescope brought distant moons into focus, Newton's prism exposed the invisible secrets within a single beam of light. And these secrets would soon become the key to exploring not just the Earth's atmosphere, but the very composition of the stars. If Newton revealed the colors hidden within sunlight, Christian Huygens sought to understand how light danced through the skies. In the late 17th century, the Dutch mathematician and physicist turned his attention to some of nature's most enchanting spectacles: rainbows and halos. Huygens began with a simple question: how does light create such perfect arcs of color after a storm, and those ghostly halos that ring the sun or the moon on frosty nights? Through careful observation and elegant mathematics, he discovered that the answer lay in how light interacts with water and ice. Rainbows form when sunlight enters a raindrop. It bends, bounces inside the droplet, and refracts again as it exits. This bending splits the light into its spectral colors, painting the familiar arc in the sky. Halos, meanwhile, occur when light passes through tiny hexagonal ice crystals in high-altitude clouds, bending at specific angles to form glowing rings. Huygens didn't just describe these phenomena. He uncovered the physics behind them. His work demonstrated that light moves as a wave, bending and scattering as it encounters obstacles. In doing so, he connected the beauty of rainbows and halos to the underlying law of optics, forever changing how we view the interplay of light and atmosphere. But while Huygens had uncovered how light painted the colors in the sky, one question remained: why was the sky blue? By the 19th century, the question that had puzzled poets and philosophers for centuries still lingered. Why is the sky blue? It wasn't until John Tyndall, an Irish physicist with a knack for uncovering the secrets of nature, decided to take a closer look that the mystery was finally unraveled. Tyndall's answer lay in the scattering of light. In his laboratory, he used a glass tube filled with fine particles to mimic the atmosphere. As he shone a beam of light through the tube, he noticed the shorter wavelengths of light, those at the blue end of the spectrum, scattered more easily than the longer wavelengths, like red. This scattering made the blue light spread in all directions, just as it does in the sky. But Tyndall didn't stop there. His experiments also explained why the sky turns fiery shades of orange and red at sunrise and sunset. As the sun dips low, its light travels through more of the atmosphere, scattering away the blue light entirely and leaving the warm colors of longer wavelengths to dominate. Tyndall's discovery wasn't just poetic, it was practical. His work paved the way for understanding how light interacts with particles in the air, helping scientists study the composition of gases and aerosols in the atmosphere. Yet his insights left scientists wondering, if light could reveal why the sky is blue, what else might it tell us about the air we breathe? And so light became a tool not only for understanding beauty, but for uncovering the invisible workings of the atmosphere itself. By the early 20th century, scientists had begun to realize that light wasn't just a way to study the sky. It could help predict the weather. At the forefront of this revolution was Wilhelm Bjerknes, a Norwegian physicist and meteorologist who believed the atmosphere could be mapped and measured with precision. Bjerknes approached weather prediction as a problem of physics. Using equations to describe the motion of air and water, he developed mathematical models that explained how weather systems evolve. But to make those models work, accurate data was essential, and light became a key part of that solution. Instruments like barometers and thermometers gave snapshots of atmospheric conditions, but light revealed more dynamic details. By measuring how sunlight interacted with water vapor, clouds, and particles, scientists could track temperature, humidity, and wind patterns over vast distances. And remember that prismatic light of Newton's? Well, spectroscopy allowed meteorologists to detect subtle changes in atmospheric composition, helping to refine forecasts. Bjerknes' work transformed meteorology from a mix of folklore and guesswork into a rigorous science. His models didn't just predict rain or sunshine, they explained the formation of cyclones and anticyclones, the behavior of jet streams, and the movement of storms across continents. Light, it seemed, wasn't just a tool for understanding the atmosphere, it was a way to see what was otherwise invisible. And while its role in predicting the weather was profound, it was just the beginning. The same light was poised to transform how we understand something far closer to home, the human body. So far, we've used light to show us how we see, the surface of the moons around Jupiter, the phases of Venus. We're using it to track storms and map the sky. But perhaps its most extraordinary journey has been inward, into the human body. And believe it or not, this path begins with Newton's scattered light. Spectroscopy, the technique born from Newton's discovery, turned out to be more than a tool for science. It became a way to see what lies underneath our skin. Every substance absorbs and reflects light differently, creating a unique spectral fingerprint. By studying these patterns, scientists realized that they could use light to uncover the body's secrets. Take pulse oximetry. This tiny device clamped on a fingertip shines light through the skin and measures how much is absorbed by oxygen-rich blood. The result? A quick, non-invasive check of oxygen levels that saves lives every day. But it doesn't stop there. In labs, light is used to analyze tissue, searching for tiny signs of disease, cancer for instance, before it can take hold. By shining light on cells, doctors can detect subtle differences in how healthy and diseased tissues scatter it. These tiny clues, invisible to the naked eye, can lead to life-saving early diagnoses. Then there's fluorescence spectroscopy, where special dyes light up problem areas like a glowing trail. It's like light becoming a guide showing doctors exactly where to look. And it all began with Newton's prism. But for now, let's return to the sky, where light is helping us uncover mysteries not within ourselves, but beyond our world. By the late 19th century, scientists had realized that light wasn't just a way to study things on Earth. It could unlock the secrets of the stars themselves. Using spectroscopy, they discovered that rainbow-like bands of light from distant objects held clues about their composition, temperature, and motion. It all started with a simple idea. Every element absorbs and emits light at specific wavelengths, creating a unique spectral fingerprint. By analyzing spectral lines from starlight, scientists could identify the elements present in the star, even though it was light years away. In the 1920s, this technique reached new heights thanks to Cecilia Payne-Gaposchkin. She used spectroscopy to prove that stars are mostly made of hydrogen, a discovery that completely reshaped our understanding of the universe. Light wasn't just illuminating the stars, it was telling us their story. But it wasn't just stars that left their mark on light. As scientists began studying the light passing through planetary atmospheres, they realized that those special fingerprints could reveal something even more extraordinary: the hidden worlds beyond our solar system. For most of history, planets beyond our solar system existed only in the realm of imagination. Then in 1992, astronomers made a stunning announcement. They'd found not just one, but two planets orbiting a distant pulsar. These weren't Earth-like worlds. They were scorched, battered survivors of their star's violent collapse. But they were the first exoplanets we'd ever confirmed. Soon after, in 1995, came the discovery of 51 Pegasi b, the first planet found orbiting a sun-like star. Nicknamed Hot Jupiter, it was a giant gas world, its surface temperatures reaching searing levels as it whipped around its star in just 4 days. At first, these planets were little more than dots on a chart, detected by their gravitational tug or the dimming of starlight as they transited their stars. But then scientists realized they could learn much more by analyzing the light that passed through their atmospheres during their transits. Using spectroscopy, they split that starlight into its component colors and looked for the telltale signatures of gases. The results were astonishing. Water vapor, methane, and carbon dioxide were all detected on distant worlds. These weren't just dots on a chart anymore. They were places with weather, clouds, and chemical compositions. Every time light passed through an atmosphere, it brought back a story. Some spoke of blistering heat, others of swirling haze. And with every story, one question loomed larger. Could these gases contain the fingerprint of life itself? Light had unlocked the atmospheres of exoplanets, and it wasn't done yet. The next step? Using it to uncover not just what's there, but what's happening. We're used to storms here on Earth. Blizzards, hurricanes, and heat waves shaped by familiar forces like sunlight, water, and wind. But storms on distant exoplanets are something else entirely. Thanks to light, we can now peer into their turbulent atmospheres, and what we found is nothing short of breathtaking. Take WASP-76b, a gas giant where temperatures soar above 4,000 degrees on the day side. Light passing through its atmosphere revealed traces of iron vapor, metal boiled into a gas. And that's not even the most astonishing part. As the planet spins, fierce winds carry the vapor to its cooler night side, where it condenses and falls as molten iron rain. Or consider HD 209458b, where escaping hydrogen gases create a colossal tail trailing behind the planet, like a comet in orbit. Light also uncovered the extreme weather of HD 189733b, where winds reach speeds of 5,400 miles per hour, 7 times the speed of sound, and clouds of molten glass are whipped across the sky. How do we know this all? It's all in the light. By analyzing the starlight reflected and absorbed and scattered by the exoplanet's atmosphere, scientists can map its temperature, chemical composition, and even its weather systems. These storms, though unimaginably alien, feel oddly familiar. Like the hurricanes and monsoons on Earth, they're driven by heat, pressure, and rotation, universal forces acting on a cosmic scale. In every storm we observe, light shows us the character of these worlds. It transforms distant planets from dots of data into places vivid and alive with motion. And with each discovery, we get closer to understanding what makes a planet unique, or perhaps what makes a planet home. For centuries, humanity has gazed at stars and wondered, are we alone? Now, with light as our guide, we're closer than ever to finding out. Spectroscopy has turned into our most powerful tool in the search for alien life. By studying starlight as it passes through atmospheres of exoplanets, scientists can look for biosignatures, gases like oxygen, methane, and even ozone that might suggest the presence of life. On Earth, these gases are shaped by living processes. Could they mean the same thing on a distant world? The James Webb Space Telescope is already at work, hunting for these faint clues. Its powerful instruments can detect the tiniest shifts in light, revealing the chemical makeups of planets orbiting stars hundreds of light years away. In 2023, Webb detected carbon dioxide on a planet outside our solar system. Just a hint of what's to come. But the search for life isn't just about science, it's about hope. Every spectral line, every faint fingerprint in starlight carries the possibility of answering a question as old as humanity itself. If we find even a trace of life's handiwork on another planet, it would transform our understanding of our place in the universe. It's humbling to think that the journey from shadows on a wall to alien worlds has been guided by the same force, light. From Alhazen's experiments to modern spectroscopy, light has always been more than illumination. It's been a bridge, connecting us to the mysteries within and beyond. And so, we continue to listen to the whispers of light, wondering if somewhere, across the vastness of space, someone or something is looking back.